recording. Let's see.
1 second, because it's glitching.
Get my screen up and running, and then we can go. All right. Can you see my screen on my iPad?
Yes.
All right, cool. All right. Let me change this paper right quick. All right. So again, today, what's today? The 24th. So today we're talking about conjugation. So conjugation is a property that you find in pi systems. And I say pi systems because you need more than one pi bond in order for conjugation to be possible. Right. So sometimes you'll hear it described as alternating double and single bonds. So alternating double and single bonds. That's one way to describe it. I always try to make it, something you can remember. So think about it like a fraternity or a sorority. It would be pi, sigma, pi, right? That's the pattern that you have to see in order to say that something is conjugated. And then another way to think about it, a more extensive definition is and I have handouts for this, but I didn't download them. So we'll use those on Friday. So don't panic. So a more extensive definition is a p orbital on every carbon. All right, that's another definition of conjugation. So something that's fully conjugated will meet this definition. And I'll show you some examples in a minute. So something that's fully conjugated, we'll say if something has a p orbital on every carbon, then we can say that it's fully conjugated. So an example of a conjugated system would be something like 1,3-butadiene. Come on, Russell, get your mind right. All right, and that's what we're going to be studying in this section is conjugated dienes. A diene is just two alkenes, right? Di meaning two, ene meaning alkene. So we're going to be looking at dienes mostly in this section. So 1,3-butadiene is an example of something that's conjugated. And you can see you have that pattern, right? Pi, sigma, pi. It's like an alternating double or pi and sigma bonds, because you can have a triple bond system that can be conjugated to something like this, like 1,3-butadiene. So you have a triple bond here, separated by a sigma bond like that. And it would be 1,3-butadiene. Well, ion means triple bond and di means two, right? So this is an example of a conjugated system, and both of these will be considered fully conjugated because you got p orbitals on every carbon. But the most, I guess, the most stable and the most well-known fully conjugated system would be something like benzene, right? Where you have here so benzene, and again, you can see the pattern. Even though it's a closed cycle system, you can see that pattern, right? Of pi, sigma, pi, Excuse my little Greek letters. I can get the pi, but sometimes my sigma is suspect, right? All the way around that ring. All right, so when we talk about conjugation, you know, it's all well and good. And let me show you an example of a non-conjugated system. So a non-conjugated system would look like this. Right, so something like just a regular alkene, right, like ethylene. You need at least 2 pi bonds for conjugation to even be possible. Or something like this. So like 1,4-pentadiene or pentadiene, right? Keep on to put a B right there. Right, 1,4-pentadiene. You can see here you got the pattern is not present. So you got pi, you have sigma. Fix that, sorry about that. Sigma, you got sigma, and then you have pi, right? So you don't have that pattern of alternating double and single bonds, right? So these are examples of systems that are non-conjugated. So let's talk about this in more detail, right? What does it mean? What does this conjugation stuff actually mean? Right, on a structural level. All right, so can somebody tell me what makes up a pi bond? Anybody? I thought you were unmuting to tell me. All right, that's okay. So what is a pi bond? What's a sigma bond? How do you get a sigma bond? Anybody?
In a sigma bond, just a regular bond.
A single bond, yes.
Yeah.
But how is it formed? How do you form any bond?
Electrons.
Yes, sharing electrons. And how do you share electrons? Think about it. Where are the electrons located? Are they just hanging out, or do they have a location? Aren't they in orbitals?
Yes.
Yeah. And you share electrons by overlapping orbitals. Is that right?
Yeah.
So remember in part 1 when we talked about sigma bonds and pi bonds and hybridization and all this other stuff. So when you make a sigma bond, you overlap hybridized orbitals. When you make a pi bond, you overlap unhybridized p orbitals. Do y'all remember that from part 1, or recall that when we talked about it? All right, so each one of these carbons in this 1,3-butadiene is sp2 hybridized. Let me put it underneath there. And it's sp2 hybridized, each one of them, right? And so in that diene, each one of those carbons has a p orbital attached. Not attached, but each one of them has a p orbital on it. Let me move these down. All right, so each carbon is sp2 hybridized, and each carbon has a p orbital. I'm not going to shade them, or I'm not going to worry about shading them yet. I just want you to see the fact that there's a p orbital on each one of these carbons, right? Anybody disagree with that? All of your pi bonds are made up of unhybridized p orbitals overlapping and sharing electrons. And everybody should remember the shape of a p orbital, right? We call it a dumbbell. It's a dumbbell shape. Right? So this is an example of a conjugated system. And if we compare that to a non-conjugated system, let me show you that. And then we're going to use this information to talk about why conjugation is actually special and what it does, right? And there. Right? So this is non-conjugated. The top structure is conjugated. So you look at the top structure, there's a couple of things that stand out. Number one, the bond length here between these two carbons is compressed. Right, it's a compressed bond. So those two carbons are actually pulled closer together. Right, these two carbons right here. And the reason is because they both sp2 hybridized, and electronegativity increases with the amount of S character. Is that right? Y'all remember that? sp3 is 25% S, sp2 is 33% S, sp is 50% S. And as you increase the percent S character, you also increase the electronegativity. So those two carbons in the middle are actually pulling on each other and shortening that bond length, right? So what that does in the case of a conjugated system, when you compress that bond angle the bond length between those two atoms, you actually turn that conjugated system into a system rather than two separate pi bonds, right? Because those two p orbitals in the middle can overlap. Right, so it's not just two separate pi bonds. It's actually one system that's made up of 4 p orbitals. In the case of this conjugated diene. Are y'all following that? Anybody got any questions about that? You can't do that down here.
So basically, you're talking about the conjugated portion. Basically, it's compressing the bond length, and when it does that, creating the system, not just It's creating the system basically, not just another carbon.
Yeah, because those two orbitals in the middle overlap. And if they overlap, that means that they can share electrons, right? So conjugation actually adds to a system. If you compare a conjugated system and the same system that's not conjugated, it actually adds like about 4 kilocalories of stability. So it decreases the energy by about 4 kilocalories, which is a lot. When you think in molecular terms, that's a lot of energy. So that conjugation turns that from a 2 separate 2 pi systems to a 4 pi system. So this is an example of a 4 pi conjugated system. Right, and that also ends up changing the reactivity, right? It changes the way that system interacts with other molecules. It changes if it's a nucleophile, it changes the way it acts as a nucleophile. If it's an electrophile, it changes that as well. But this is an example of what we call a 4 pi conjugated system. And we call it 4 pi because it's 4 pi electrons, because there's 1 electron in each one of these orbitals. Right? So it's a 4 pi system because it contains 4 pi electrons. So it contains 4 pi electrons. All right. Any questions? Anybody not catching it? Say something. All right. So let's talk about these conjugated systems in terms of what we call molecular orbital theory. All right. So let me give you a little bit of that, and then I'm gonna give you 2 examples of reactions that conjugated systems do. That they do a lot of different reactions, but we're only going to discuss 2. So,
What is that supposed to say, Dr. Russell? What theory?
say again. Molecular orbital theory. I'll write it
Okay.
out. I gotta text my son back. I don't know what unless he called and telling me they're not gonna play today. Sorry about that. Daddy duties. You never stop being a parent. Once you have kids, you're a parent forever. All day, every day. If you're a single parent, it's even more responsibility. All right. So let's talk about molecular orbital theory. So this is just basically a way to describe these conjugated systems and understand their reaction, like how they react. Right? It's a theory that was developed by Einstein, contributed to it. Several other scientists contributed to it, but what it's basically saying is a couple of things. The first thing is that when you add up atomic orbitals, so atomic orbitals combine to form what we call molecular orbitals. All right. So you got atomic orbitals like p orbitals, like s orbitals. If you combine them, then you get what's called molecular. I'm going to show you what this means in a minute. Molecular orbit. The second concept that molecular orbital theory kind of encompasses is that electrons have both wave and particle-like properties. So it's called a wave-particle duality. So they have wave-like and they have particle-like properties. All right, and because of that, we can it helps us to think about how these I'm just going to take it and extend it, how these conjugated systems, how they react, right? And we can kind of explain their reactivity based on molecular orbital theory. So let's go back to our 4 pi system, right? So we got 4 atomic p orbitals in that system. All right, got 4 atomic orbitals. All right. And so what molecular orbital theory says is this, that if you got 4 atomic orbitals, then that should generate 4 molecular orbitals. Right, so I'm gonna show you what this means with a 2-pi system first, before we get to the 4-pi and draw the diagram for it. Because I don't want to overwhelm you with the 4-pi system right away. So let me show you what this means with a 2-pi system. So let's say I have an alkene, right? Just an alkene like ethylene. Right? If I just have a simple alkene, you can see right away that it has a pi bond and a sigma bond, and that the pi bond is actually made up of, just like we just talked about a second ago, 2 unhybridized p orbitals. So this has a p and that one has a p, right? And so when we look at that, we think about the fact that you got 2 atomic orbitals. So for the 2-pi system, you have 2 atomic orbitals. That means you should generate 2 molecular orbitals, right? Because the sum of the atomic orbitals is equivalent to the sum of the molecular orbitals. Are you following that?
No, not understanding.
Yeah. So how many P's do we have right here? We got 2 P's. Yes, you agree with that?
Yes.
So we got 2 P's. The p orbitals, we call those atomic orbitals, right? We haven't mixed them or combined them with anything. They're just atomic orbitals. They're orbitals that sit on that atom. But if we add them together, do y'all recall when we did hybridization and how we took the S and the P or PX, PY, PZ, and we added them together, and depending on how many of those we added, that determined how many hybrids we got. So like for SP3, we took the S and all 3 Ps, and we got 4 SP3 hybrids. Do y'all recall that from part 1? Or like for SP2, we took the S, and we're talking about hybridization on carbon. We took the S, and then we took the S, and then we took the 2 Ps, added them together, and we got 3 hybrids. Do y'all remember that from part 1?
Yes.
Yeah. So it's the same. It's kind of the same idea. If we take 2 p orbitals and add them together, then we should get 2 molecular orbitals. And so let me show you what they look like, and then we're going to talk about some of the other parts, like the particle wave duality and all this stuff. So, and then keep in mind, this is a 2-pi system. So that means we have how many electrons? We got 2 pi electrons, or 2 electrons involved in that pi system. All right, so there's an electron here and 1 here to make that pi bond, because every bond is composed of 2 electrons. All right. So let's look at it. So and we're going to describe these molecular orbitals using what's called a molecular orbital diagram. Right, so these are my 2 molecular orbitals. What it really is the number of ways you can combine those 2 p orbitals, right? If you got 2 p orbitals, then there's going to be 2 different types of molecular orbitals that you can put together. If you got 6, then you'll get 6 molecular orbitals. If you got 8 p orbitals, you're going to get 8 molecular orbitals, so on and so forth. So these are my 2 molecular orbitals, right? This is in this energy diagram, right? We got a couple of things we need to identify first, and then we're going to make all of this make sense, right? So this is what we call the first harmonic, right? That's the wave. Now we're talking about the wave-like properties of those electrons, and I'll explain that in a minute. All right, so that's the first harmonic, and this is the second harmonic. Anybody remember hearing this in physics when you're talking about waves? and frequency and wavelength and all that stuff? No. You just took the A and ran, huh? All right. So it's first harmonic, second harmonic. And if you go up again, it'll be third harmonic. Go again, it's fourth harmonic, like that. All right. So how many of you remember Hund's rule from general chemistry? Anybody? There's gonna be a big gap on YouTube. Somebody needs to say something. Nobody remembers Hund's rule? All right. When I'm filling, let me refresh your memory. If I'm filling up two orbitals, and one of them is higher in energy than the other one, how do I put the electrons in? Do I give each orbital one, or do I fill up the low level before I go to the next level?
Do you fill up the low level before you get to the
Yeah.
next one?
Yeah, you fill up the low level degenerate orbitals before you add any electrons to the next set of orbitals. So in this case, both of my electrons are going to be in this molecular orbital right here, and then the top molecular orbital is going to be empty. Are y'all following that? Does that make sense? Because the energy, I should have said this earlier, but the energy is increasing in this direction. All right, so your energy is increasing vertically. So when you fill up your molecular orbitals with electrons, which again, this is going to help us to understand how this system is going to react with another species, be it a nucleophile or an electrophile. All right, so when I fill up the orbitals, I put my electrons in that lowest energy level before I touch the top energy level. All right. And then when I look at the two orbitals, both of them, these are my molecular orbitals. Again, I call this one the HOMO. And then I call the top one the LUMO. HOMO stands for highest occupied molecular orbital. Highest occupied molecular orbital. Write that down where you are. Right. I don't know if I have room. Let me see if I can squeeze it in here. So highest occupied molecular orbital for the HOMO, and then the LUMO is the lowest unoccupied. And we're going to talk about that. So don't worry about it if it's not clicking right away. The lowest unoccupied molecular orbital. It's unoccupied because it does not have any electrons. Okay, does that make sense? Are y'all following? If you lost or you're not following, say something.
You said it was unoccupied, it doesn't have any electrons?
Yes.
Okay.
Mm-hmm. So we know a lot about this 2-pi system and what the molecular orbitals look like. And the reason we got 2 molecular orbitals is because we started with 2 atomic p orbitals. And they can combine 2 different ways. So that's why you see 2 molecular orbitals. All right. The last thing I want to talk about with the diagram is the wave-like character of these electrons, right? The wave-like character. So if you remember if you took physics and you remember, let's just say I have a wave like this. Or if I have a wave here in the first harmonic, I'm just going to abbreviate that. And I'll put right in the first harmonic, the wave never passes through 0. Right, so the wave never changes sign. So the sign of your wave doesn't change. Right? And then if you go to the second harmonic, right, you got one node here where the wave does change signs. So you have one sign change. Anybody remember that from physics when you took physics? I'm gonna stop asking questions. All right. So if you look at and how, so let me kind of back up because I don't want to rush. How does this apply to orbitals, right? How does the wave-like part apply to orbitals? Well, every p orbital, when you think about a p orbital and how it's constructed, this actually, it has a application. This wave theory has an application. Right, so a p orbital shaped like this, am I right? What's the middle part called in that p orbital? What do we call that? Anybody remember from part one? I said I was gonna stop asking questions, but it's a habit. Just try to make sure y'all are not asleep. All right. Anybody?
Honestly, I forgot.
All right. Thank you for your honesty. It's called a node. Anytime a wave passes through zero, it's called a node. Now let me ask you this question. When you think about an orbital or a p orbital, is it real or is it imaginary? Any orbital, S, P, D, F, like any orbital. Is an orbital tangible, something you can hold in your hand and
I
touch?
think
No.
it's tangible.
Yeah, it's actually. I heard somebody say no, then I heard somebody say yes. An orbital is actually not tangible. It's just an equation of the path of an electron, right? And each orbital has a different equation. So orbitals are actually graphs of equations. All right, so it's not tangible. It's just a graph of an equation that depicts the path of an electron. Right, so when you think about a p orbital, right, and you think about it being an equation, equations can have a sign, right? It can be a positive or it can be a negative, right? And so when you think about the p orbital, the node is where that equation passes through zero, right? And what happens if a wave passes through zero or something passes through zero? Anybody? What happens to the sign if something passes? What happens like if you're doing a graph of a straight line or you're doing something on the Cartesian plane? What happens on the right side of zero and left side of zero? Anybody? Then they go from positive to negative, like you have a sign change.
Right.
Yes.
So that's what happens in this orbital, right? So I'm going to shade one part, leave the other part unshaded, because and the shading is not indicative of the location of the electrons. What it means is that the sign of that equation changes when it passes through the node. That's all it means. The electrons can be in either side, they just can't be in the middle. They can't be at the node. They can be in the top lobe or the bottom lobe, but they just can't be in the node. Are y'all following? So how does this apply? If you think about this as a wave, right? If it's in the first harmonic, then you can have 100 p orbitals in that first harmonic, and they all gonna have the same sign, because in the first harmonic, in an MO diagram, the sign of the wave never changes. So the wave is gonna look like this in the first harmonic. And what that also means is that your p orbitals are gonna maintain their signs as well. Right, so this is going to be shaded, and that's going to be shaded, because since the wave never passes through zero, the signs on those p orbitals will never change in that first harmonic. Any questions about that? All right, and if you follow the pattern of a wave in the second harmonic, you can see that the wave is going to pass through zero once. What happens to the signs of the orbitals in that case? Should they both be the same, or should they be different?
It should be different, right?
Different.
They should be different. That's exactly right, because the wave passes through zero. That means that the sign of the wave changes, and then it also means that the signs on your orbitals have to change. Make that a little more aesthetically pleasing. Right? Any questions about that?
So
This two-part. Go ahead.
So you're saying when it goes through the first node, the first harmonic, the top parts of the p orbital going to be shaded because that's where the energy is.
They're only shaded. The shading is only telling you the sign of the lobe. That's it. So when the first harmonic, the sign of the wave never changes, and so the signs on your lobes will never change, right? Like I said, you can have 2 orbitals, you can have 4, you can have 6, you can have up to, you can have 100 orbitals. That those top lobes are all gonna have the same sign, because that wave never passes through zero in the first harmonic. Then if you go up to the second harmonic, you got 1 node, one time where the wave passes through zero. So let's say you had 100 p orbitals. In the first harmonic, all 100 of those orbitals are gonna be the same. And the second harmonic is the node is gonna come at the 50th orbital. So 50 of them are gonna have the same sign, 50 of them will have the opposite sign. Are you following?
No.
Because the wave has to be symmetrical, right? So it's not gonna cut, somewhere, at some weird location. When it passes through zero, it's gonna be a symmetrical pass, right? That's why I didn't show that here like this. Let me change the color of that. That's why I didn't show it passing through on this side, right? Everything has to be symmetrical. So let me make that other example clear. So let's say I had 10 p orbitals, right? If I can fit them in, they have to be 8. Let me shrink them down. Add one more. Let's say I had 8 p orbitals like that. You following? If I had that in the first harmonic, but the wave never passes, everything up here is going to be the same sign. The sign's not going to change, because the sign of the wave doesn't change. If I put it in the second, if I had the same number of orbitals in the second harmonic, the wave is going to cut once, but it's got to be symmetrical. So it's going to basically cut right in between those 8 orbitals. And then when that happens, the signs will change also. Right, and this is applicable to any pi system. It's the same pattern, the same wave pattern for any pi system.
The
Right,
shape of the p orbitals is based off of the first harmonic and the second harmonic.
it's based on the sign of the wave. If the wave is above the line, then everything is going to be, and I guess we can say it'll be positive. And then if it's below the line, everything changes to negative. Let me show you. Let's look at the 4 pi system, and then we can make this make more sense. So I'm gonna leave that, but let's talk about the how this applies to a 4 pi system, and then hopefully it'll start to click. So in a 4 pi system, if it's conjugated, and what that means is you have a 4 pi conjugated system like this, like 1,3-butadiene, and again you got 4 p orbitals, 4 atomic orbitals. How many molecular orbitals would you expect?
4.
4. So 4 molecular. So you basically have 4 combinations of those 4 p orbitals, right? And how they can combine. That's what that means, right? So I'm gonna start here in the diagram. I'm gonna copy this just for the sake of time, but you can write it out later. But I'm gonna copy it. So that's here. I know it looks like magic here, right? You got 4 molecular orbitals. Are y'all following that? Because I started with 4 p orbitals, and I can combine those 4 p orbitals 4 different ways. That's going to give me 4 molecular orbitals that I'm working with. Right? Anybody not see that? Just like up here, we started with how many p orbitals? We started with 2 atomic p orbitals. And so because of that, we have 2 ways that those orbitals can combine. So you get 2 molecular orbitals. All right. So let's go back down to the 4 pi system. Where's the first harmonic? Is it the very bottom or the very top? Remember, energy is increasing in this direction.
Is it the very bottom?
It's the very bottom. Just like this part never changes. That's the first harmonic, second harmonic, third harmonic, fourth harmonic. Now, how many? So let's look at the waves, right? In the first harmonic, the wave is like that. Never passes through 0. Is that right? So what do the lobes on the p orbitals look like in the first harmonic? Are they all shaded?
Mm,
All right.
There-
Before you answer, what did it look like on the 2 pi system in the first harmonic?
we're talking about the second harmonic, right?
We can't do that one until we do the first one. What did the first harmonic look like here?
The top of the p orbitals are going to be shaded.
On both of them, right?
Mm-hmm.
And that if I had that applies to if I had 100 of those in the first harmonic, that the sign of those lobes is never going to change. So down here, this is shaded, that's shaded, that's shaded, and that's shaded. They all got the same sign because the sign of the wave never changes. So the sign of your lobes is not going to change. What about in the second harmonic? How many times does that wave pass through 0?
I think twice, right?
How many times did it pass through up here? Where this is 0, right here. Let me change colors on that. That's 0. How many times did that wave pass through 0? If it's 0 in the first harmonic, it's a pattern. That's what I'm trying to get you to see. If it's 0 in the first harmonic, and the second harmonic is only going to pass through once, and the third harmonic is going to pass through twice, and the fourth harmonic is going to pass through 3 times. It's a pattern. So if it passes through 0 times here in the first harmonic, that doesn't change. When you get to the second harmonic, it's still going to pass through 0 one time, but it's got to be a symmetrical pass. So it's not going to cut here and leave these 3 hanging out. That's not how it works. It's got to be symmetrical. And so I'm going to pass through 0 here, right there, and like that, right? The wave is only going to pass through 0 one time. So you get 1 node. So how would that be shaded now? What do you think? Compared to the first
So
harmonic?
Right.
you
Okay.
shade the first 2 of the p orbitals, and then
Mhm.
the last 2 of the second half.
Yeah. And why did we do it that way? Because the sign of the wave changed. So the sign of the orbitals changed. Right? Because again, the shaded, unshaded part is just dealing with the sign of the orbital. It's not dealing with where the electrons are located or anything like that. It's the sign of the orbital. So if the sign of the wave changes, then the sign of the orbital also changes. What about if we go to the third harmonic? How many times is that wave going to follow the pattern? It's 0, then it's 1. Then if you go up to the next energy level, what's the next? How many times should it pass through there?
Twice.
Twice. And symmetrically, right? So we're going to put a node right here. We're going to put 1 there and 1 there. Are y'all following that? So I'm cutting this symmetrically, right? So the wave is going to pass like this. Right? It's going to go here, pass through 0, here, like that. Because again, this is that particle wave duality. We think about the orbitals as waves, and the electrons, where the electrons that are in the orbitals are particles, right? So we're saying that the electrons can have both particle and wave-like properties. So it's the particle wave duality. So the wave is now set. Now we just need to do what? That's shaded. Everybody agree? Ooh, that's sloppy. Sorry. And this is what? What do these 2 look like in the middle?
Wouldn't they be shaded on the bottom?
Yes. And then we go back to here when the wave goes back above 0.
Mm-hmm.
Are y'all following? Is it starting to make sense at
Okay.
all? All right, what about in the fourth harmonic? If you need a way to remember how many times the wave passes through 0, just subtract 1. So in the first harmonic, 1 minus 1 is 0. So the wave never passes through 0. Second harmonic, 2 minus 1 is 1. So the wave passes through once. Third harmonic, 3 minus 1 is 2. So you got 2 nodes. So in the fourth harmonic, right, you're going to have 3 nodes, three places where the wave passes through 0. And it's an even number of orbitals, so the node is not going to fall on top of an orbital. That can happen, but it only happens when you have an odd number of orbitals. Right, so then my wave looks like that, not like that. Here, right, boom, 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 like that. Now, tell me this, what's the shading look like there?
So for the first p orbital, you're going to shade the top of it.
Mm-hmm.
The second p orbital, you're going to shade the bottom part of it.
Mm-hmm.
The third one, you're going to shade the top of it.
Yep.
Then the fourth, the bottom.
Yep. That's exactly right. Right. And this matters when you start doing reactions, right? Because one of the other takeaways from molecular orbital theory that I didn't talk about, but I'm gonna add it in real quick before we stop. Is that, let me see if I can do this real quick. Shrink that and get it out of the way. One of the other really critical parts of molecular orbital theory is that your MOs, right? Your MOs are going to predict reactivity. Right, and it's going to react either through the HOMO or the LUMO. That's how you predict the reactivity of a system. You can look at the diagram, look at where the HOMO is, look at where the LUMO is, and then you'll know how it's going to react. If it's an electrophile, I'm gonna put this right here. It's going to react through the LUMO. If it's a nucleophile, it's going to react through the HOMO. All right. So let's go back down here and let's label our HOMO, LUMO, and then we're going to wrap up. So which one of these, first of all, how many electrons are we dealing with? All right, we're dealing with 4. Man, it's too thin. Sorry about that. We're dealing with a 4-pi system. Right, so that means that there are 4-pi electrons. So we got 4 electrons, we got 4 orbitals. How are we gonna fill it up though? Are we gonna put 1 in each orbital? Or we're gonna use Hund's rule? We gotta use Hund's rule. Right, you can't put electrons in a high energy orbital until you fill up the low energy orbital. Right, all right. Which one of those is the HOMO? What do you think? HOMO meaning highest in energy, occupied meaning containing electrons, highest occupied molecular orbital. What do you think? What's the HOMO? This is, right? Is that the highest filled orbital? If you look at the 2 orbitals that are filled and energy is increasing vertically upward, that's the highest occupied molecular orbital. And then the LUMO is here. It's empty and it's lower than the empty one above it. So if you think about HOMO and LUMO, think about the molecular orbitals, like each molecular orbital as a floor in an apartment building. So the highest floor that contains tenants is the second floor, the second harmonic. The lowest floor that contains tenants or that contains no tenants, in this case, is the third harmonic. All right, so the HOMO or LUMO, that's how we predict the reactivity. That's why molecular orbital theory is so important, because it helps us to understand how these systems interact. All right, we got to stop because it's right at 9:59. All right, any questions? Anybody got any questions before we log out?
We're meeting in class on Friday.
In class, you mean, what do you mean? Yeah, you mean, do we have class?
Yes.
Yes.
Are you gonna do the recitation on Thursday or no?
I need to let me look at my schedule right quick, because sometimes I have stuff scheduled on Thursdays. I've been screwing up. I apologize to y'all for that. I'm a bad professor, the worst in the world. I don't think I have anything tomorrow evening. It's only because of baseball season. There's always something going on. But anyway, yeah, we can do a recitation tomorrow. I'm just gonna do one note at 7.
Do we still have a test on Friday?
Yeah.
Oh, do you know how
Yeah.
the test is given yet?
Say again.
You know how the test is going to be given?
What do you mean?
Mm,
I'm still contemplating that. I want to
Okay.
do, since I can't do like file submission questions on this and with this Blackboard Ultra, I'm thinking about creating like two separate parts. One part multiple choice, and then the other part will be a file submission. So, because if it's just all multiple choice, that's like giving it away. That's free money, and I want you to actually put your pen to the paper and actually show me something too. So it'll probably be two parts, but it'll still be due on Sunday, and it'll still be the same format. It'll be on Blackboard.
Okay.
All right. Any other questions? All right. So we're gonna log out, and I'm gonna stop recording, stop screen sharing. And yeah, I'll see y'all on Friday, God willing. We'll see you on Friday at 9. All right, y'all have a good day.
Have a good day, Dr. Russell.
All right, you too.